Let's begin our review of the June 2023 Regents Chemistry exam. Under the description, there is a link to the time code to every single question. So if you just want to move to a certain question, please look under the description to do so. If not, want to stay along for the entire ride, let's go. So let's be crazy and start in order with number one. So number one. Which phrase describes the nucleus of the atom? Okay, well, this is really important that you should know the basics of the atom at this point, but Ernest Rutherford had a very famous gold foil experiment. And what he did is he actually discovered the nucleus of the atom. He shot alpha particles, which we should now know, okay, are helium nuclei, and he saw that most of them went right through. And the reasoning is very simple. Most of the atom is empty space. Occasionally, these nuclei of helium atoms called alpha particles deflected, very occasionally. And why would that be? Well, they got close to that atomic nucleus. He discovered the atomic nucleus. And the atomic nucleus is a small part of the overall atom, but it's positive. That's why they deflected. Positive helium nuclei, of course, their nuclei also, they're positive. So positives and positives repel. You should know that the nucleus has an overall positive charge. Ernest Rutherford in the gold foil experiment discovered that because he shot positive particles and they what? Deflected away from the positive nucleus. So when you shoot a positive toward a positive, they will repel themselves and deflect away. So it's very important. Now, we also discovered later on that in this nucleus, where the entire mass of the nucleus exists, there was also neutrons. Okay, so the entire mass of the atom is due to protons and neutrons. Now, as the word describes neutrons, they don't have a charge. So again, if we look very carefully, and again, I'm over teaching this so you completely understand this, helium has an atomic number of 2 and a mass number of 4. This atomic number of 2 means 2 protons, which are both +1. And of course, there's a mass of 4, which means what? Well, there are 2 other particles in the nucleus that have the same mass as a proton, and that would be a neutron. And that's what an alpha particle is, 2 protons and 2 neutrons. It's a helium nucleus. But the entire, nucleus is a +2 charge in this case. We call that a nuclear charge. So these are kind of things that you should know as I'm going over the background. So obviously, which phrase describes the nucleus of an atom? It has an overall positive charge because the other particle in the nucleus that has the same mass, the neutron, has no charge. Okay, so that's why number 1 is your answer. All right, moving on to number 2. So number 2, which of the 2 particles each have a mass approximately 1 atomic mass unit? Now, 1 atomic mass unit sometimes is written as AMU, or it's written as just U. It's a relative scale. You can't put, a proton, neutrons, or electrons, or positrons, whatever these choices are, on a regular scale. So just understand that those are just units made up to measure the relative amount of these tiny, tiny particles. But they're basically saying in this question, which 2 particles, have about the same mass? And if you didn't see number 1, we understood that protons and neutrons do. Now, I can just tell you that, but you can also go somewhere to remind yourself. So if you go to table O, and a lot of teachers don't utilize this table for atomic structure. They just use it for nuclear chemistry. Let's go to table O, and I'll show you how you could have reminded yourself about that. Now, it's written table O, but I kind of like the Brooklyn feel. Table O! Okay, so table O is what we're going to call it here. All right. Yeah, if you don't know, table O is your friend. And notice we have this alpha particle with Ernest Rutherford shot. It's a helium nucleus. And what you should know is that the top number is the mass number. So if you get up close and personal with this, this is the mass number of the particle, and this is the charge of the particle in table O. Okay, now, if we look at the bottom, or toward the bottom, we have a neutron with a mass of 1 and a proton with a mass of 1. Notice they have an H there because H is the atom that only has 1 proton. So that's why they have a nucleus of what? Of a hydrogen is a proton, because a proton has 1 proton and has an electron, but just a nucleus of hydrogen is just a single proton. That's why it's there. But the bottom line is, what I'm trying to show you, my friends, in chemistry, is that they both have 1 mass unit. So protons and neutrons have approximately the same mass. Notice that a positron, as we saw in the choice, is given a 0. Okay, then that's not 100% accurate. It's very, very small. It's about 2,000 times smaller than that of a proton and neutron. So we give it a 0 because when you compare it to a proton and neutron, it just doesn't have enough mass to be significant. A beta particle, by the way, is another word for an electron. And if you notice, for an electron, although not in the choice, it's given a 0 too, but we know it's also about 2,000 times lighter. Notice its charge is what? -1 for an electron. Notice the E there. So some nice things given out here in table what? Table O. Okay, so let's go back. So clearly table O can remind you that the proton and neutron both have the same mass. Okay, and of course you should know they're located in the nucleus. Everything outside the nucleus is that empty spaces. I'm trying to reinforce these important concepts. So let's go back to the test. All right, so which 2 particles have the same mass? Table O tells us a neutron and a proton. So number 3 is our answer. Moving on to number 3. So number 3 states the wave mechanical model of the atom describes the location of electrons. Okay, the wave mechanical model is the current model of the atom. It's what we're currently using. So this is really important that you understand how the model of the atom kind of developed over time. We knew, or there was evidence that John Dalton that utilized either from his own experiment or other experiments that there were tiny little particles that were responsible for pressure. And so if these little particles hit your hand, they make pressure, or they hit your hair, they make the hair go back. So they thought the particles were solid spheres initially. J.J. Thomson discovered that, wait a minute, there's these negatively charged particles in the cathode ray experiment. It's called the plum pudding model. These electrons were haphazardly placed, okay? And so when we go to the next model, Ernest Rutherford, he discovered the nucleus where the protons, didn't know about neutrons yet, but the mass of the atom was in the nucleus. Electrons were somewhere outside of it. They weren't really organized. Niels Bohr had that famous, model, the first quantized model, where you had these positive protons. There's neutrons in there too, but more important, these electrons orbited the nucleus in shells or orbits, and their distance to the nucleus determined their energy levels. Right? He was the first to talk about the quantized, the energy level, the exact energy level requirements that electrons have. Electrons, of course, that exist closer to the nucleus because they feel the positive of that nuclear charge more. They have lower energy. Electrons that exist farther away, and they could be the outermost, could be the valence, they have higher energy because they're farther away. They don't feel that positive. Okay, so you need to know that the circular paths that everyone wants to think about, all right, in these questions is the Niels Bohr model. That's not the current model of the atom. Okay, the idea that the electrons are loosely packed in the nucleus is in no one's model. Electrons are never in a nucleus. The nucleus was discovered by the gold foil experiment by Ernest Rutherford, shooting the alpha particles. So this was never discovered, electrons in a nucleus, because the nucleus was positive because of the protons. All right. And electrons densely packed in a nucleus for the same reasoning does not make any sense. So a lot of people would pick 3 here because they always think of the atom as electrons going in circular orbits, and all chemistry teachers use this Niels Bohr model to explain the energy levels, and sometimes we do it too much. So Niels Bohr was correct that the atom was quantized, had exact energies based upon the electrons, distance in these orbits. What he was wrong that the electrons didn't travel in circular orbits, but he was right that the electrons did have distinct energy levels based upon shells, based upon distance. So that's really a reason why a lot of people would pick 3, but it's not the correct answer. The wave mechanical model states that, hey, we've got a nucleus, okay, that's positive, whether you understand that neutrons were there or not yet. And these electrons, okay, were in these areas based upon their idea that they make an electron cloud. We don't know exactly where they are at any one time, and we use something called probability. Now, this is not in your question, but you should know wave mechanical model uses probability. That's kind of a catchphrase to discover where the atoms are. Okay, and 2, it also treats electrons acting as particles and, more importantly, as waves. Now, people say, what kind of waves do they make? Well, waves of probability. It's kind of a difficult way to understand the current model, but that's what they talk about. They act as waves. And the 3, and the biggest thing is that electrons don't exist in orbits, but because Niels Bohr took the atom to a new level, and the current model still uses most of what he discussed outside of the orbits, they just use the same word and added orbital. Okay, so orbital is a catchphrase that tells you something about the current electron cloud model. By the way, the wave mechanical model could also be called this electron cloud model too. All right, so be aware of the catchphrase orbital, probability, and waves for the wave mechanical model. And that's why choice 4 is the best answer here. Moving on to number 4. Number 4, when ground state electron in an atom moves to an excited state, the electron does what? Okay, first of all, I hear the word atom. I always think neutral, so it's not an ion. Okay, the ground state means kind of like if you're grounded at home, you're in trouble. You're grounded. We used to say that. Okay, I'm getting older now. Maybe I don't say that anymore, but grounded means you couldn't go anywhere. Ground state means the lowest energy. So the lowest energy an electron can have. Now, the lowest energy would be electrons that exist closer to the nucleus, because a nucleus is positive because of the protons, and it feels the what? The negatives outside. Now, an excited state would be where, man, this thing's got energy, highest energy. Now, highest energy would mean that you're farther away from the nucleus, okay, or that you were given energy to pull away. Let me give you an idea of what I'm talking about. So we know the nucleus is positive because of the protons. There's neutrons in that very small nucleus, but we know that there are shells, okay, and we're just going to use the circular orbits as an example, and I'm going to draw 2 shells. Okay, now these are based upon distances, so we're going to have an electron existing here and an electron existing here. Okay, now we should know, based upon proximity, electrons closer to the positive. Remember, electrons are negative, protons are positive. And this one being closest, this means that this shell right here is going to have the lowest energy. So the lowest energy. And you should know lowest energy means stable. Things that are stable in your life, you don't think about lowest energy, but you probably think about they're always there. If you've got a big rock on your yard, or things that are stable stay in that state because they don't have enough energy to change that state. Okay, so people that you can depend upon, you can think about as being stable. They're always going to be there for you. Okay, now things like electrons that are farther away from the nucleus, like this electron here, we're going to say have higher energy. Okay, and we say that's unstable. If you've got high energy, that normally means that you're going to do something with that energy. Okay, and so electrons that are farther away are unstable. Now, back to the question, why do I care? Well, because in the question it says, when a ground state electron moves to an excited state, what does electron do? Well, okay, so if I've got an electron that's closer to the nucleus here, all right, let's talk about this electron here. And if it is given energy that gets it exactly to this point, that's why it's quantized. It can't just go there. It needs to have a minimum amount of energy, and it can leap to this shell. Okay, it needs to absorb energy because it's got to overcome this positive. So there was an absorption of energy when you move away. You need energy to move away from the positive, my friend, in chemistry. And then this electron will be excited. And the reason why it's excited is because it's in a high position, and wait for it, okay, there's no longer electron in this position there, okay, there's an ENT. I think I erased the white there. So there's no longer an energy, there's no longer an electron here, because it was what? It jumped, okay, and there is a low position available for an electron, and things in nature like to move back to lower positions. A rock on top of the hill moves to the bottom. Water moves from high to low. Energy moves from high to low. So now we've got something with a high energy, and okay, it'll eventually jump back. So any case, back to the question, when a ground state lowest energy electron, which we now know is close to the nucleus, moves to an excited state, the electron had to do what? It had to absorb energy. Excited means having high energy. And it moves to a higher energy state. Okay? So it, again, for you, this was a ground state right here. Ground. Lowest energy. This is excited. It moved to a higher energy state. Okay? So it's important you understand that. All right, so number one is number 4, I should say. Number 1 is the correct choice for number 4, because absorbing energy means you're going to pull away, okay, and be farther away and exist in a higher energy orbital. You have to have this diagram in your head. And as I'm here, why not go over it? Eventually, this high energy electron is going to jump back to its low energy position. And because it has high energy being farther away and it's going to go to low energy, it's going to give off that energy in the form of light or spectrum. And that's where we do the bright line spectrum. The type of light that gives off gives us an inclination of how much energy is being released. Okay, any case, question 4 is number 1. On to number 5. Number 5, which statement describes a chemical property of iron? Okay, whether you know iron or not, iron of course is Fe on the periodic table, but you don't need to know any of that. The chemical properties and its relative, or its its antithesis or opposite, I should say, is the physical property. They love to pit things against itself on these tests. So the physical property versus the chemical property. I should put verse there. That's what this question is about. And because this is a multiple choice question, my friends, in chemistry, you can always figure out which one is the one that's different. Okay, but the chemical property is a one about changing into a new substance. Now I say new substance, but a chemical reaction is going to have a new chemical formula. Okay, so in a chemical change, we're going to break bonds and we're going to reform them. And we're going to make products that have a different chemical formula than the reactants. Okay, case in point, I take hydrogen gas and I take oxygen gas, okay, and I'll need 2 of these particles, and it's going to make 2 water molecules. This is a chemical change. I've got 2 hydrogens, I've got Let's do two hydrogen particles here. These are called elements. Diatomic. Oxygen's diatomic too, but I need one here. These guys react with each other, and what do they make? Well, they're going to make two water molecules that have a different arrangement. Okay, and they're going to look like this. So we're going to break bonds right here, and we're going to form new ones. And we're going to make a brand new chemical formula. We had H2, we had O2, and now we have the compound water. Water is very different than oxygen gas and hydrogen gas. They have new properties. So a chemical property is really testing whether or not you can change into something new by breaking bonds and forming new ones. So malleability is the property. Can you take iron, heat it, and shape it? Of course, iron is a metal, and it's a property of metals. It is malleable, but shaping iron doesn't change its chemical formula. So that, my friends, would be a physical property. Iron conducting electricity is about how well it has free moving electrons, but it conducting electricity doesn't change the compound. Copper is in our wire. Think about that. Electricity flows through copper. It's not changing. Okay. Iron has a higher melting point. Okay. The melting, freezing, and boiling point are also physical changes. This is huge. Why? Well, Fe solid going to Fe liquid, okay. Are we changing the chemical formula, party people? No. So therefore, it's not a chemical change. So melting point, condensation point, freezing point, vaporization, all the phase changes are physical. And the only choice here that makes sense is ion reacts with nitric acid. Its ability to react like hydrogen and oxygen react, okay, to make something new. So reacting with another compound to make something new is a chemical change. That's why number 5 is 3. On to number 6. Number 6. Diamond and graphite are two forms of solid carbon. That means the chemical formula of diamond, okay, is carbon solid, and graphite is also carbon solid. That's right. All right, so we know diamond is something that we can wear in jewelry. Graphite, of course, is something that we use in our pencils. People say they're lead, but they're not. They're graphite. So there are two forms of solid carbon. Okay, now clearly diamond and graphite have different properties. All right, so if they have different properties, I say this statement over and over again. Structure is king. We know that if you change the chemical formula if you compare molecular formulas, a different arrangement of atoms in compounds will give you different properties. We also know from organic chemistry, if we change the structure with the same chemical formula called an isomer, will have different properties. So we know that the structure has an effect on the property. So in this case, because they have the same chemical formula, it must be the structures are different. Different crystal structures have different properties. So that's why 1 is your answer. Okay, structure is king. So if you change that physical crystalline structure, you will change the properties. Like I said, diamond and graphite are exactly, okay, the same atoms bonded to each other, but they bond in a different arrangement. Will give them a different set of properties. Okay, so these are called allotropes. Okay, but nonetheless, this is a classic question that comes up a lot. All right, structure is king. Change the structure, change the properties. On to number 7. Number 7, which substance? Substance. We should need to know what that is. A substance, my friends, in chemistry is either going to be an element which differs by their proton number, right? So element or a compound. And a compound is two or more different elements bonded together. So which substance can be broken down by a chemical change? Well, we know that elements cannot be broken down, okay, because they're the simplest form of matter. Elements are a group of the same type of atoms. For instance, all right, if I've got neon atoms, okay, they are made up of the same number of protons. But if I have water, everyone likes to use water, okay, you notice it's an H bonded to an O to what? We can break water down into what? The individual elements. So what we're looking for, guys, in my question is a compound. All right, we need something that we can break down. So if you don't know what a compound or a name of the elements, table S, my friend, is the most underutilized table. If you go to table S, you'll find cobalt listed as an atom. You'll find krypton listed as an atom. Manganese as an atom. In your organic part of your course, you should understand that ethane is a compound. Remember, eth is 2 carbons from table P. Ane means a single bond between them. Okay, so carbon must make 4 bonds. 1, 2, 3, this is 4. This carbon makes 1, 2, 3, 4. And so this is C3H8. Okay, which is a saturated hydrocarbon, but more importantly, it's 2 or more different what? Elements bonded. It's a compound, and compounds can be broken down into their individual elements, whereas 1, 3, and 4 are just elements already. Okay, so it's important that you understand that question. Sometimes they'll flip it, which substance can't be broken down. So if it's can't, okay, remember this is can, we'd be looking for elements. Elements are the simplest form of matter in this course. And of course, compounds are 2 or more different elements bonded. All right, hopefully that helped there. So so ethane, of course, is the answer. And on to number 8.